So let's go. Let's come back. So now, so wait. So now it's time for talk of Professor Dusa McDuff from Department of Mathematics from Barnard College, and today she's talking about an introduction to embedding problems in symplectic geometry. So thank you so much for Professor Dusa for accepting the invitation to give a talk. We are more than happy to hear you, and you can start whenever you wanna. Thank you.
Thank you very much. It's a great pleasure to talk in this conference honoring Paul Schweitzer. I'm really sorry I can't be there with you. There was a time in the 1970s when I was interested in foliations and flows and was very familiar with Paul's work at that time. But my interest moved towards symplectic geometry and have remained there. So our paths have somewhat diverged since then. The methods I use are now rather different from those other methods, though they're related via contact homology to Hamiltonian flows on the boundary of the objects I consider. But mostly I'm just looking at the geometric problems to do with the nature of a symplectic structure. So I know you're not specialists in symplectic geometry, and I'm going to begin by giving you an elementary introduction to symplectic geometry. And now let's see if I can move the slides. Now, wait a minute. The slides are not moving. There we are. So here is the plan of my lecture. I'm going to give you a brief description first of symplectic geometry. So it's a rather elusive geometric structure that can be put on an even dimensional space. And after talking about that, I'm going to talk a little bit about the symplectic embedding problem in general, and then in particular about the Fibonacci staircase and various other new developments. So to begin with, what is a symplectic structure, symplectic geometry? Well, I like to contrast it with Euclidean geometry, which of course makes measurements using a symmetric bilinear form, the dot product on Euclidean space. In symplectic geometry, you use a skew symmetric bilinear form, such as this standard form, and it's on an even dimensional space in which you pair the first two vectors and then the second two vectors and so on. And in general, on a general manifold, it's an even dimensional smooth manifold. A symplectic form is a differential two form that locally looks like the one I've given above, omega 0, in suitable local coordinates. So it's in fact, it can be any closed two form whose top power is a volume form. So it means in dimension 2, it's an area form. And what you're studying are area preserving diffeomorphisms. And they have many interesting properties. For example, they have more fixed points than arbitrary diffeomorphisms. And those properties extend to symplectic geometry in higher dimension. They don't extend to volume preserving diffeomorphisms, but Arnauld realized that they do extend when carefully chosen things do extend to symplectic diffeomorphisms. And his conjectures, which date from about the 1960s, have been very influential in symplectic geometry. Now, let's look at the standard form in a little bit more detail in 4 dimensions, because I'm going to be talking in 4 dimensions mostly. So there we have a sum of area forms. And what you're doing, you take a little piece of surface, S is 2-dimensional, and you project it on the x1, y1 plane and take its area, and project onto the x2, y2 plane and take that area and add them up. So that's what you can measure. And this measurement is a rather flabby measurement because it's a closed form. So if you have a little piece of surface in R4, the measurement actually only depends on the boundary by Stokes's theorem. So if you deform your surface, you get the same, but keep the boundary fixed, you get the same measurement. So it's very different from Euclidean geometry, where if you think of drawing a line between 2 points, the length of that curve definitely depends on that curve, not just the 2 endpoints. So it's a very different kind of geometry. But it's very related to physics, because in physics, the pair xi, yi represent the position and velocity of a particle in one dimension. And the measurement you're doing is somehow a measurement of the entanglement of those. So it's a bit obscure what it's doing geometrically, but it is incredibly fundamental in basic classical physics, the symplectic form. Now, in general, so I say, you have on a smooth manifold, a symplectic structure is a closed non-degenerate 2 form. And there are many, there's a uniqueness of symplectic structure locally, but then there are lots of symplectomorphisms. There are lots of diffeomorphisms that preserve the symplectic structure. And one way of getting them is to take a function on your manifold, H, called a Hamiltonian function, and then that generates a flow, phi ht, that actually preserves the symplectic form. And that these transformations are called symplectomorphisms. So you get many symplectomorphisms just because each function has such a flow. And how this works is as follows. You take your function h, that gives you a one form dh. I think I can point to it perhaps with my cursor. Disappear. Anyway, you get a one form dh, and then you use the symplectic form omega to get a pairing with a vector field. So you use the symplectic form instead of the Euclidean inner product to get a vector field xh. And then the claim is that if you flow along that direction, that xh gives you a flow, and the equations you get are what are called Hamiltonian's equations. If any of you have studied classical mechanics, those are the equations you study in classical mechanics. That dx by dt is dh by dy, and dy by dt is minus dh by dx. And for example, if you take just a quadratic, a half of x squared plus y squared, you find that dh is x dy plus y dy, x dx plus y dy, and xh is points in the direction y in the x direction and minus x in the y direction. It gives you a rotation, which preserves the circles h equals constant, and that's absolutely standard. The Hamiltonian flow preserves the level set. And there are many, many other symplectomorphisms, because you can actually do this if h depends on time. And that means that symplectic geometry is very flexible in some ways, because of many, many transformations of a symplectic manifold that preserve the form. But there's also interesting rigidity, because there are certain things that are preserved. Like when you're flowing in 2 dimensions, you preserve area. But there are many more interesting things that get preserved, and that's what's one of the interesting things about symplectic geometry. If you look at a symplectomorphism, what does it preserve? What can you say about it, and what is just sort of flexible? Now, one way of seeing this is through the work of Gromov, who in 1985 asked, suppose you have a ball in Euclidean space, a standard round ball, and you look at its image under a symplectomorphism, what can you say? And in 2 dimensions, you can't really say anything, because if you take any closed region U, which is diffeomorphic to a disk and has the same area as this disk D, then you can find an area preserving transformation from one to the other. So there's nothing interesting in 2 dimensions. But in 4 dimensions and higher, they certainly are interesting things. So if you look at the ball, which now when I'm talking about the ball, I'm measuring its size by this parameter A, which is an area. So it's the area of a 2-dimensional slice of this ball. It's pi r squared if r is the radius. And so if you take this ball of size A and you take a cylinder of size big A, so where you constrain the first coordinate so that it lies in a disk of area big A and the other coordinates are free, then Gromov proved his non-squeezing theorem that there's a symplectic embedding of the ball into the cylinder only if the size of the ball is less than the size of the cylinder. There is, of course, a volume preserving map that takes the ball into any very thin cylinder, because you can squeeze in the first 2 directions and expand in other directions to compensate. But you can't do that in the symplectic setting. So that was the first non-trivial result of this kind. And you might think it's just a curiosity, but in fact, it's very important. It leads to the notion of symplectic capacity. So you say, what's a symplectic capacity? Well, it's a kind of measurement of the size of a set, which is invariant under symplectomorphism. So here I've defined one, which is the size of the largest ball that will embed in U. And it suddenly is in a symplectic invariant of U. It's essentially two-dimensional, because if you take the cylinder, that's got infinite volume, but it's got finite two-dimensional capacity. And what you can prove is that if you have an orientation preserving diffeomorphism that preserves capacity, then it's essentially its symplectomorphism. It preserves a symplectic form up to sign. So this very innocent looking property, this non-squeezing property of a ball, is enough to characterize what symplectic geometry is. It tells you what transformations preserve the structure up to a sign. So it's very fundamental. And of course, you can ask, well, what other obstructions are there to symplectic embeddings? You can also ask, there's a whole interesting theory about, suppose you look at homeomorphism, just topological, things which are topologically one-to-one and onto, and ask that they preserve a capacity. What can you prove about those? So you get away, you have a topological theory of symplectic, preserving a symplectic structure, completely getting away from the fact that the symplectic form is a differential form. So you've got out of the differentiable category. Lots of unknown questions about that. Now I want to move on to talking about what I've been doing recently, which is embedding ellipsoids. So you have embedding a ball was Gromov's result. So now let's talk about embedding a slightly more complicated shape. And the simplest kind of shape, that sort of nice shape, is an ellipsoid, because that's still characterized by it's the boundary of a quadratic form. And on it, the Hamiltonian function generates a flow which lives on the boundary. And if A over B is irrational, there are only two periodic orbits. There's the orbit around the disk of radius A, of size A, and there's an orbit around the disk of size B, and then all the other, it's basically a simple harmonic motion with two incompatible periods. So it's got interesting dynamics on the boundary. Now, Hofer conjectured, he had many ideas about when one ellipsoid might embed into another, but eventually he came up with this numerical criterion saying that if you want to know whether one ball embeds in another, there's a set of numbers you can look at associated, and one set of numbers has to be less than the other set. So let me explain that. So NAB is a set of all numbers which are integral combinations of A and B, non-negative integral combinations of A and B. So KA plus LB with KL non-negative, and you arrange that with multiplicities, because sometimes numbers occur more than once, but you keep all those numbers and put them in increasing order. So if you start off with 2 and 2, then you have 0, which of course is 0 times A plus 0 times B. Then you have 2 twice, because you have once A and then once you have B. And you have 3 lots of 4, because you have 2A, you have A plus B, and you have 2B. And then you have 4 6s and 5 8s and so on. So you can just write out. It's a beautiful sequence. You can look at the sequence for 1 4. So then you have 1 2 3 4, but then 4 can come twice, because you've got 4 times 1, and you also have 4, and you have 5 ways of 2 ways of getting 5, 2 ways of getting 6, 2 ways of getting 7, and 3 ways of getting 8, because you now have 2 4s, 4 plus 2 4s, 4 plus 4 1s, and 8 1s. And you can repeat, you can look at, you can extend these sequences but prove very easily that the sequence for 1 4 is place by place less than or equal to the sequence for 2 2. Therefore, the conjecture would say that you can embed the longer ellipsoid, the 1 4 ellipsoid, into the ball, because if A and B are equal, you just have a ball. Now, these numbers, Helmut didn't come up with this conjecture just out of nothing. These numbers are the actions of the generators of embedded contact homology, which is a homology associated to the boundary of a symplectic domain, which is a contact manifold. And it's got these periodic orbits, and you can define a kind of Floer theory or gauge theory related to these numbers. And these are the actions of the generator. So you're saying something about the behavior. You can capture these inequalities by dynamical behavior on the boundary of the regions. It's got nothing to do with the inside. So I proved this conjecture, and I'll explain a little bit about how this works. Actually, Hutchins developed the theory of embedded contact homology, and what he showed is that if an embedding exists, then the NAB has to be less than NCD. So he proved that if you have an embedding, then you have the inequality. But the other way around, well, it needs some geometry. You can't just do it by looking at dynamical flow. So that's the other side of it. Now, what I did with Schlenk was look at what this means if you try and figure out when an ellipsoid embeds into a ball. So this is the sort of easiest kind of this problem. You define a function called the capacity function, which is Cx, which is defined with the infimum of the size of a ball into which the ellipsoid E1x embeds. So x is the x we're assuming is bigger than 1, so that's sort of the eccentricity, if you like, of this ellipsoid. We standardize the ellipsoid, so it's got one axis of size 1 and then one axis of size embed x, and then we inflate the ball by saying it's got capacity mu, and take the smallest capacity that will into which you can embed the ball. So that's a perfectly well-defined function. And, we found out that it had a much more interesting structure than we thought it would. That one would, obviously it has to be non-decreasing. There is always an obstruction to do with volume, because if the ellipsoid embeds into the ball, the volume of the ellipsoid has got to be smaller and less than or equal to the volume of the ball. And the volume of ellipsoid is a constant times x, while the volume of the ball is a constant times mu squared. So you've got to have x less than mu squared. So that means that mu is bigger than the square root of x. So that gives you a lower bound. That's the volume constraint. But what we found is that if we were less than the golden ratio to the 4th power, we found this infinite set of obstructions, which meant that the function had this piecewise linear aspect, very regular piecewise linear aspect, where the numerics are completely based on the Fibonacci numbers. So they're just very definite numbers come in here. And the structure of this function is that when it's increasing like this, it's increasing on a line through the origin. So this is the origin, it goes through the point 1, 1, and it goes through the point 2, 2, and then you have this line of slope 1. Then it's constant, this is constant, and this point is actually on, this is the volume obstruction, so it's on the volume obstruction. And then we have another step where it goes up on the line from the origin again, and it goes up to its next peak, and then it's constant until it hits the volume curve, and then it goes up and again. So it just has this very, very regular behavior. And when you get, if x is big enough, so in fact, when it's bigger than 17/6 squared, then there are no obstructions except for the volume. So it's completely, there's no obstructions in that part of it. And then in the middle bit, there's some transitional region where sometimes there are obstructions and sometimes there aren't. Felix and I completely calculated what that was, but it's not so interesting because it doesn't have any really understandable structure, except that it's not always above the volume line, and it's still sort of piecewise, it's either piecewise linear or it's the volume. Now, this we calculated completely in dimension 4, and I was going to explain to you more why you get the Fibonacci numbers, where all this comes from in most of the rest of the talk. But if you ask what happens in dimension 4, that's a pretty good mystery. Nobody knows what the right answer is. We do have some obstructions, but the obvious analog of Hofer's conjecture is false. So the obvious analog, you have now ellipsoids have got 3 ABC, and you've got an ellipsoid EABC, and you've got another one DEF, and you could look at the set of numbers and say the first set of numbers has to be less than the second set of numbers, and that's a necessary and sufficient condition for an embedding. But it's not even necessary, because if you can geometrically construct embeddings. The first one was done by Guth, of E1SS into something which is controlled at just above 3 in the first 2 coordinates, and it's very big in the third coordinate. But because S can be as big as you want, there's no numerical condition like Hofer's condition that's going to deal with that. So nobody knows what the right answer is. And so people have, at the moment, have moved on to slightly other questions, because if you haven't something, you have no idea what to do with, you move on to something else. Now, let me try and explain a little bit what goes into this calculation. So first of all, I mean, the connection with number theory comes via toric models. So just a little brief reminder about what toric models are. So, a ball or an ellipsoid are very symmetric. You have an action of a S1 times S1. And if you think of them sitting inside R4, then you can use polar coordinates in R4. So you take Z1 and Z2 to be complex coordinates and map them to T1, T2, which basically is a radius squared, pi Z1 squared, pi Z2 squared. So you're forgetting that this forgets the torus action. And if you do that, then an ellipsoid, which is given by a quadratic equation in the 4-dimensional coordinates, maps to a triangle, because pi Z1 squared is just T. So you get the ellipsoid looks like a triangle, and a ball looks like what we call a standard triangle with sides. I mean, the ellipsoid, you have the sides are of AB, but if it's a ball, A, it's equal to A, and you get what we call a standard triangle. So the standard triangle has just got sides 1 and 1. And then you have to realize that in doing this transformation, we've chosen a particular set of coordinates, and you can change these coordinates by an integral affine transformation. So we could replace our coordinates. In other words, replace them. We've chosen, basically what we've done is we've got a 2 torus, and we've identified it with S1 times S1, but there are lots of ways of doing that. So we could use a different identification for the torus and then get a different model. So if we have this here is an ellipsoid with one side of length 1 and one side of length 3, and I've cut it up into 3 triangles, but each of these triangles is affine equivalent to the first one. So each of these you can embed a ball in. There's something called a trainer trick that allows you to say that a symplectic ball embeds in each of those. So if you look at that picture, you can see that the torus T1, the triangle T13, you can cut into 3 standard triangles. And what that tells you is that you can embed 3 disjoint balls into the ellipsoid E13. Perhaps you have to take open balls, just so you don't have to deal with the boundary. But this is a way of understanding how you can embed unions of balls into ellipsoids. Now, you can do this very generally. So if you take any triangle with sort of integral triangle, you can decompose it into standard triangles of different sizes, where a standard triangle is equivalent to TCC, so just some multiple of the one T11. So here's a picture where I've started off with T53. So I've got a triangle, it's got size 5 here, and it's got height 3. And I'm decomposing it into triangles. One triangle of size 3, a standard one. I put a standard triangle of size 2 there for this one. And then I put 2 standard triangles of size 1 in, so this triangle and that triangle. And that would be a decomposition of this triangle T53 into standard triangles. And, you know, if you're thinking of toric images, then of course, the toric image of a ball is a triangle. But if you're thinking combinatorially, this picture here, when you're cutting up this triangle, is entirely equivalent to a picture where you cut up rectangles into squares, and that's much easier to see. So if we start off with a rectangle of size 5 and 3 and 5, then we take one square of size 3, put a square of size 2, and then 2 squares of size 1 there, and that gives you a decomposition, which is combinatorially exactly the same as the one above it. And you can see that because if you take this picture of the rectangle and remove that point in the corner and collapse these sides, but keep all the internal points of reference in the right ratios, then you see that you get from the second picture to the first picture. So really, when we're doing these decompositions, it's much better to think in terms of rectangles instead of triangles. You'll get the same answer. And so that's just a sort of thing you can do. So it's saying, okay, you can take a triangle, which is represented by an ellipse, and you can embed balls in it. You can make it basically a disjoint union, essentially decompose it into balls, using up all of it. Now, this decomposition is related to continued fractions. So if you have a rational fraction P over Q, I don't know what number theorists call it, but I called it the weight expansion. And you can decompose, if you have, say, 25 over 9, so you have 9 as the height and 25 as the length, and you do this thing of decomposing it into 2 squares of size 9, then you've got 7 left over, but only room for 1 of those. And then you've got 2, you have 3 2s, and then you have 2 1s. That gives you this decomposition here. And amazingly, that corresponds to the continued fraction decomposition of 25 over 9, which is 2 plus 1 over 1 plus 1 over 3 plus 1 over 2. And these numbers, 2, 1, 3, 2, which give you the continued fraction here, are the multiplicities of the weight. So I think these 9s and 7s and 2s are the weights, are the sizes of the squares, and the multiplicities are the things that give you the coefficients of the continued fraction. And, if you don't believe me that 29 over 5 is this sum, you just work out from the bottom. You say, well, 3 plus a half is 7 halves, and you take its reciprocal, so that's 2 sevenths. 1 plus 2 sevenths is 9 sevenths. Take its reciprocal, you get 7 ninths, and 2 plus 7 ninths is 25 over 9. So this is a completely general fact that, any rational number gives you a decomposition of this kind. Now, so I've explained how you can take an ellipsoid and cut it into balls. And then the amazing thing is that if there's a theorem that tells you if you can embed the balls, then you can embed the ellipsoid. That's one of the things that sort of key steps. So if you have a fraction which has this normalized weight expansion, so the normalized weight expansion starts with 1s instead of with lots of copies of Q, you just divide everything by Q, then the claim is that the ellipsoid E1P over Q embeds into a ball if and only if you can embed the disjoint union of balls into the bigger ball. So that you've cut up the ellipsoid into balls without any wastage, and there's an equivalence of the embedding problems. And that, to prove that, you need to know something about the theory of J-holomorphic curves. I can't quite go into that, but that's a theory that Gromov introduced in his paper, and that sort of is a foundation for a lot of this work. But anyway, this tells you a way of trying to embed ellipsoids into balls. You just try and figure out when you can embed balls into balls. Now, you might think that's not an improvement, but in fact, in the 90s, people worked out when you can embed a set of balls into a ball or something like that. And the theorem is that you can embed a union of balls into a bigger ball, B for mu, if and only if you can find a symplectic form on the n-fold blowup in a particular cohomology class, the class has got to be such that on the line in CP2 it integrates to mu. So that's this CP2 mu is a copy of CP2 where the form takes the value mu on the line. And then you've got all these exceptional divisors which have the sizes given by these weights. Now, this would be very mysterious, you know, if you don't know a little symplectic geometry. So the process of blowing up in algebraic geometry is you take a point and you replace it by all the lines through a point. So that's a completely general thing you do in algebraic geometry to help you get rid of singularities. You sort of blow them up and look and see what you have. Now, if you're in 2 dimensions, a set of all lines through a 2-dimension in CP2 is a one complex dimensional object, and it's what's called an exceptional curve. It's smoothly like a copy of S2, and it has normal bundle -1, and it has a completely regular kind of neighborhood. So if you meet one of these, you can get rid of it and replace it by a point. That's the process of blowing down. In symplectic geometry, if you meet one of these curves, which is a holomorphic curve with a -1 self-intersection number, because you're in a symplectic manifold, it will have some area. The symplectic form will evaluate to some number on it. And when you blow it down, you don't blow it down to a point, but what you do is you blow it down to a ball, because it turns out a ball of size, well, however big the size of your sphere was. So that was something that actually is due partly to Gilliman and partly I exploited it a lot when I did sort of basic theory about rational symplectic form manifolds, that if any exceptional curve is sort of equivalent to a ball. So that's why, you know, if you embed the balls, you can sort of remove them and collapse the boundary to an exceptional curve by the Hopf map and get a symplectic form in this class. And then you prove that there's a reverse, it's a one-to-one correspondence between this with, well, you do have to use some gauge theory. You do have to use Taubes' proof that there's a unique symplectic form in CP2 and things like that. So it's not a totally trivial proof. And then Lee and Lee, who were working with gauge theory, showed that what is the set of classes on a blow up of CP2 represented by a symplectic form? Well, it's got to have positive volume, so alpha squared has to be positive. And then the other condition is that alpha must integrate to something positive on all the exceptional divisors in the blow up. So if you have a blow up, we've got these standard exceptional divisors which correspond to the points you've blown up, but there are lots of other ones sort of given by, for example, if you take CP2 and you blow up 2 points, then the line through those 2 points becomes an exceptional divisor. So you have a new class, a new exceptional line class. Or if you take a conic in CP2, which goes through 5 points, if you blow up those 5 points, you get a new exceptional divisor in that class. So there are lots of exceptional divisors, but there's this beautiful characterization of the symplectic cone that you only need your class to integrate positively on all exceptional divisors, and then you'll have a symplectic form. Now, the analog of this kind of result in algebraic geometry or Kähler geometry is absolutely not known. I mean, you can say, okay, we've got CP2, I blow it up lots of times. What's the Kähler cone of that? And that is not known. That's a more complicated problem. But in symplectic geometry, those difficulties go away. So we have this beautiful description. And so now you see, if we're trying to embed ellipsoids, we have a sort of a problem, geometric and algebraic. You really want to know what are the homology classes of the exceptional divisors in the blowup, which are going to affect, you see, you've got these, if you pick your ellipsoid, you pick P over Q, you have a particular set of weights there. So you have a particular kind of class you're looking for, and you have to figure out which exceptional divisors are the relevant ones to obstruct the existence of that that symplectic form. And the fact is that there's this, if you're mapping into a ball, then the coefficients come from Fibonacci numbers. And if you're mapping into something related to a ball, like a ball when you've blown up a point, then you get other nice numbers. They're not Fibonacci numbers, but you get other nice numbers. So if we go back to the Fibonacci staircase and look and see what we have here, so what we found was that the exceptional classes and blowups of CP2 that gave the sharpest obstruction to embedding PQ had a particular form. So they have degree D, and then there are some of MI, EI, where the MI are they come from the weight expansion of P over Q, but they're the integral weight expansion. So you take them all multiplied by Q, so that they're all integers. And the ones that are relevant to us are where D, P, and Q are odd-placed Fibonacci numbers. Now, why that's the case, I don't know, but that is the situation. That so to give you an example, if we write down the Fibonacci numbers here, I wrote down the first few of them, and suppose we're at P over Q, which is 2 over 1. So the odd-placed ones are 1, 3, 5, 13, and 34, right? We ignore the other ones. And these give you if you look at the ratios, 2 over 1, 5 over 2, 13 over 5, they increase and they converge to the golden ratio squared. But at P over Q, actually, yeah, so those are the ratios of the odd ones. But anyway, at P over 2, the weight expansion just 1 and 1, because it's an ellipsoid with one side 1 and the other side 2. And the obstruction is just L minus E1 minus E2, which is the blow up of a line through 2 generic points. So the degree is 1 and the weights are 1. So that's a very simple example. 5 over 1 is a slightly better example. So 5 over 1, these are these are Fibonacci numbers 4 apart. And the weight expansion of 5 over 1, again, is just 5 lots of 1s. And the obstruction now has degree 2, which is the middle number here. And it's 2 minus E1, 5 exceptional classes. And that corresponds to blowing up a conic through 5 generic points. And that gives you the next obstruction. And then the next one comes at 13 over 2. So these are, again, numbers 5 apart. 13 over 2, and the degree is 5. And so the weight expansion of 13 over 2, well, we start with 6 lots of 2s, and we have, actually, this is a misprint. This should be 2 1s. We have 2 1s at the end. And the obstructive class is degree 5, and you've got 6 exceptional divisors with coefficient 2, and then 2 more exceptional divisors with coefficient 1. So that corresponds to this weight expansion, if I'd corrected that. And then the next one after that would be at 35 over 4, and it would have degree 13, and so on. So that's the numerics. So we find that those are the numerics of those obstructions here, which is quite surprising and rather beautiful. And so people started looking at other targets. You know, when do you have phenomena like this? So pretty quickly, Schlenk had some students who looked at the case. I mean, if you look at, instead of mapping into the CP2, the next obvious thing to map into is S2 times S2, where the target would look like a square. And there's a very analogous kind of staircase there where the numbers come from Pell numbers. And then after that, Michael Usher looked at, if you look at, instead of a square, you look at what's called a polydisk. So it's still the product of two-dimensional spheres, but one of them is bigger than the other. So you've got a ratio, you know, you've got one of them has got size 1 and the other one has size B. And then you look for values of B and see, do you find infinite staircases? And Usher found lots of very interesting staircases there. And I'll say a little bit more about that later. But there was another set of works by Cristofaro Gardner, Holm, Mandini, and Piras, who looked at it much more general targets. So instead of just looking into a ball or one target or something, they were looking at general toric manifolds. So typically blow-ups of CP2 by up to 5 points or something like that. And they proved a very nice general result, showing that if it did have this infinite numbers of obstructions, so, you know, they showed the function is always piecewise linear it's the maximum of the volume obstruction together with some piecewise linear obstructions. And if there are infinitely many relevant obstructions, then these obstructions have steps. They have this step form that I was describing, and the steps have to accumulate at a particular value, which is the analog of 2 to the 4th for the ball. So there's a particular number which has to be the accumulation point for a very general kind of target. And then they also conjecture that there's only a finite number of rational domains with staircases, and that these things have to correspond to monotone manifolds. So C1 being a multiple of the symplectic class. And this conjecture is very hard. It leads to some really hairy number theory, which nobody's solved. But on the other hand, there are many more examples known where there are staircases. And so with a whole lot of people, Tara Holm, Nikki McGill, Emily Moore, Grace Moore-Comber, Anna-Rita Puris, and Morgan Weiler were studying Hirzebruch staircases in Hirzebruch surfaces HB. So that's the 1-point blow up of CP2, where you blow up size B. So it's like the polydisc setup, but slightly easier, I think. And we find that the set of B, which do have staircases, has very interesting symmetries and fractal patterns. So there's lots of very interesting numerics coming from this. And McGill, Puris, and Weiler recently, we nearly computed it, apart from one sequence of values that we didn't quite deal with, so one sequence of rational values of B. But they've completed it, and they showed that indeed there really are only 2 rational values which have staircases. One is B0, and the other one is B as a third, which is the monotone case. And none of the other rational values have staircases. And there are very intriguing connections of the symmetries and what we're doing with mutations of almost toric fibrations. So that's, this problem has nice relations to other parts of geometry. And very recently, I've been working with Kyla Siegel, trying to understand the symmetries that we find. I haven't really been able to explain what they look like, because you only see them when you see a family of in a family situation. You don't see similarly, if the target is a ball, you don't see the symmetries. Only when you look at the ball as part of this whole family of Hirzebruch surfaces do you see the symmetries. And at least some of them correspond to a very basic birational transformation of CP2 that actually adapts to when you take CP2 blown up at more general points. So we haven't finished this, so I'm not going to say very much about it, but we're trying to understand the symmetries in terms of the behavior of birational transformations of CP2. And then the other symmetries that there are, because there's a reflection symmetry, which is very mysterious that we don't understand at all. But I think this is a good place to stop, so thank you for your attention. And perhaps I'll go, here are some references.
So thank you so much, Professor Dusa, for your talk. It was really nice. So let's see if the audience, if there are some questions, comments.
Hello.
Can she hear? Can Dusa hear?
Yeah, I can hear you, Steve.
Oh, do you have applications for this stuff? I mean, if the 2-dimensional stuff, embeddings, gives you all of symplectic geometry, what's going to happen with the 4-dimensional theory?
Well, this is really 4 dimensions, because we've reduced it to 2 by looking at toric pictures, right?
Yeah, I mean, are there going to be applications to the geometry of higher dimensional symplectic?
Well, I mean, we've sort of, I don't know anybody who's working on the general problem of, I mean, it's surprising. There are obstructions, to embeddings. People suddenly work on trying to understand the obstructions to embeddings. We're trying to, you can do, in higher dimensions, you can look at what's called the stabilized problem. So you can take a 4-dimensional ellipsoid times, say, R2, symplectic R2, and try and embed that into a ball times an R2. Yeah. And then, that's a stabilization of dimension, just by multiplying everything by R2 or R4 or something. And then these staircases are all incredibly stable. So they just persist under that. They don't disappear.
That is interesting.
But, you know, there are many unknown things. And this is just something that amazingly that you can calculate, right? And of course, then you can say, well, why are you just looking at embedding ellipsoids? Why don't you embed polydiscs? Suppose we take a polydisc, even in 4 dimensions, you take a polydisc and want to embed it into ellipsoid or embed that into a ball. What can you say? And that, you know, you can say some things, but these questions are just complicated and not completely resolved. Polydiscs are much more complicated in general to understand. Ellipsoids are easy because they have this, you know, they're sort of beautifully round. They don't have any awkward corners in them, and you can somehow you can cut them into balls, at least in 4 dimensions. But, you know, that argument is very 4-dimensional and doesn't work in higher dimensions. And I'm sure some of this, you know, some of this structure we find on the for these obstructions will come up in other contexts. But you know, I don't know exactly what they are.
Yeah.
Hello.
Hello.
Firstly, I just want to say that for me, I find this to be one of the most beautiful results of the last 20 years in mathematics. I've heard about this result a few years ago and I fell in love with it immediately. It's a wonderful result. It's just amazing. I don't say that often. So I just have 2 little questions. The first one is between the 4th power of the golden ratio and 17/6². I mean, do you have some sort of structure like self-similarity, or does that only occur when you look at the parameter version that you spoke about right at the end?
Well, I mean, Felix and I completely calculated what the obstructions are for mapping into the ball. And so we just found that we had the staircase governed by whatever recursion relation gives you the Fibonacci numbers. And then we found a finite number of other obstructions, which in between sort of either centered at 7, centered in between 7 and 8, which don't seem to have much, you know, they don't seem to have much structure, and we certainly haven't looked at those.
Right.
If you look at the Hirzebruch, I mean, I've spent a lot of time in the last few years looking at the question where you take a ball and you blow it up once. So this HB family, and that has a lot of amazing symmetry. So it has a symmetry. I mean, it has, you know, if you have a B parameter which does have a staircase, then the staircase has much the same structure as the Fibonacci staircase. It's governed by some recursion relation. But what we found is that we again have this notion of a perfect class, which is a class which has a center P over Q, and so it's an exceptional divisor, which now has 2 degree coordinates because it has the size of the line, and then it has the size of the exceptional divisor in the target. So there are sort of like 2 degree targets, and then you expand on the other sort of ellipsoids which correspond. Exceptional divisors which correspond to the blow-up parameter, and there, you know, again you use a weight expansion of some ellipsoid, and then that will obstruct if you choose the degree coordinates correctly, that's going to obstruct the embedding of that ellipsoid. And then, you know, so each of our classes has a center P over Q, and for the case of the Hirzebruch surface, the fundamental recursion seems to be that a pair P over Q goes to the pair 6P minus Q P. So that's a fundamental symmetry that takes you, say, from 6 over 1 going to 35 over 6, going to 204 over 35, and so on. And it's a sequence which actually converges down to it's a sequence of sort of centers of these things which converges down to the accumulation point, the point I call A min, which is the accumulation point of the 1/3 staircase. So there's this beautiful structure here, and then there's also reflection symmetries. That one of them takes the Fibonacci staircase and reflects it, because the Fibonacci staircase is the steps increase. It reflects it to a decreasing staircase, which converges to some number well, it's some number bigger than 7. It's got a continued fraction expansion of something like 7, 5, 1, 5, 1 repeated, something like that, if I remember it correctly. So it's very mysterious, that other symmetry, the reflection symmetry. I don't understand. But the symmetry, the one that takes you q going to 6p minus q over p, that one is the one that Kyler and I have an explanation for.
It comes from what, the fractional linear transformations of CP? Is that what you were saying?
Yeah, that's right. It comes from birational transformations of CP2.
Right. I have another question. I'm guessing this is probably a tall order. Is it possible for you to explain the bit that's a big mystery to me is how you... Still there?
Yeah.
All right.
I'm listening.
We lost the screen here. The bit that's a big mystery to me is how you go from finitely many embeddings of balls into an embedding of the ellipse, how you build the embedding of the ellipsoid out of finitely many embeddings of balls. Is it at all possible for you to explain the idea?
I can explain a little bit. In fact, I mean, I wrote a paper about that, which did an example. The point is that you take your ellipsoid and you can cut it exactly into balls. But if you make the cut slightly bigger, what you're actually doing is resolving. I mean, if you think of the toric picture of the complement of the ellipsoid, it's got 2 singular points at the 2 corners, and you're making a simultaneous resolution of those 2 corners. And so I mean, there is a beautiful, if you do the standard resolution of a orbifold point in toric geometry a la Fulton, you get Hirzebruch Young continued fractions. In other words, continued fractions with minus signs in. But it so happens if you take an ellipsoid, you have two related singularities at the 2 corners, and the minus singularities and the minus continued fraction expansions of those 2 corners sort of mesh together to give you the plus continued fraction expansion of P over Q. And this was known as the Riemann-Schneider staircase. And I didn't actually put the reference here, but I did write, I lectured on this in Japan once. So there's an article I wrote, a sort of survey article for the Bulletin of the Japanese Mathematical Society or something. It's on the archive, which explains this.
Okay,
anyway, so you've got these 2 resolved singularities. And so what you have, you've got a whole chain of spheres, and you want to try and embed that chain of spheres. And so you use a process called symplectic inflation. And in my original paper, I sort of sloughed over that point, and I didn't quite do it correctly. But I wrote a paper with Opstein, which did this in careful detail, exactly how. And I wrote an erratum to the paper explaining exactly how you can adapt the method of symplectic inflation to sort of, you have this chain of things which you've embedded a small ellipsoid, and all you want to do is to change the symplectic form so this thing looks big. So you take a curve and you deform the symplectic form, use it to deform the symplectic form outside the ellipsoid, so the ellipsoid fills almost all the volume.
Okay. What year is that paper with Opstein? Just so I can find it.
There's a paper with Opstein, but the original paper I wrote called Embedding Ellipsoids, it was published in the Journal of Topology, I believe, around 1910 or 11 or something.
2010.
It's there anyway.
Okay,
it's just that that original paper, I didn't give a proper proof of this non-generic inflation argument.
Okay.
And so I corrected it with this paper with Opstein, which did give a careful proof.
Wonderful. Thank you very much.
Yeah.
So any other questions? So let's thank again Professor Dusa for a really nice talk. Thank you so much. So